In this video, you will learn how to write electron configurations, draw orbital filling diagrams, and give dot diagrams for an element. You will also determine the number of valence electrons in an atom and be able to relate this to the location of the element on the periodic table. Finally, you will be able to explain why elements on the periodic table have similar chemical properties. For most of this video, you will need your periodic table, as we will be using one of the diagrams on the back. So if you don't have your periodic table, please pause the video now and grab it. The first thing we're going to talk about is how to write what are known as electron configurations and orbital filling diagrams. What these are is two ways that we can show the distribution of electrons in an atom. So an electron configuration focuses on the electrons in an atom. We already know that the electrons are not found in the nucleus, but rather they are found outside of the nucleus. Specifically, electrons fall or are found in different energy levels, and within those energy levels can be found in different orbitals. What electron configurations and orbital filling diagrams do is give the energy level, atomic orbital, and the number of electrons in a particular orbital. To help us determine the electron configuration, we are going to use what is known as an energy level diagram, which is the diagram here on the right. If you flip your periodic table over, you will find a diagram similar to this, which you will want to be using. So before we get into actually writing electron configurations, there are some rules we need to follow. Okay, so when we write an electron configuration, and as we start going through examples, these rules will make more sense. But the first rule we need to remember is that electrons enter the lowest energy level first. So if we look at our diagram here, the lowest energy level is going to be down at the bottom. And we will see that the lowest energy level is assigned a value of 1s. Okay, the 1 represents the energy level. The s represents the orbital that electron will be found in. Okay, as we make our way up, you'll see we have the second energy level, the third energy level, fourth energy level, etc. And so electrons are always going to fill the lowest energy levels first. Once that energy level is full, then it will move its way up to the next energy. So again, we start down here at the 1s. Okay, from there we'll jump to the 2s, then it'll move over to the 2p, then to the 3s, 3p, 4s. Okay, now the one thing you want to note with this is once the 4s is full, you will be jumping over to the 3d. Once the 3d is full, then we move over to the 4p, up to the 5s, etc. And again, as we start writing these, this will become more apparent. Okay, so the first rule of thumb is we start at the bottom and then we move our way up the energy level. The second thing we want to remember is that each orbital can hold up to 2 electrons. Okay, each one of the little circles is going to represent one of the orbitals, and so each circle is going to hold up to 2. So here is my first orbital. To show an electron then, we are going to use a diagonal line. So if I kind of redraw this to make this bigger. Okay, here's my 1s, so I'm going to draw the circle. In order to show an electron, we're going to make a diagonal line. Okay, second electron, we make a second diagonal line. And so an x in an orbital indicates that orbital is full and it's time to move up to the next energy level. Our third and final rule has to do with when electrons occupy orbitals of equal energy, one electron is going to enter each orbital until all of the orbitals contain 1 electron. At that point, the electrons will then start to pair up. And sometimes this is referred to as the bus rule, because if you were to get on a bus and you didn't know anyone, chances are you would sit in an empty seat until all of the empty seats were full with at least one person, and then people would have to start to pair up. So what that means is if I were to, let's say, look at this second energy level, if I had to place 4 electrons in this second energy level, I would place 1, 2, 3, 4. So notice in the 2p, I placed the 2 electrons, one in each one of those circles. If each of those circles had 1 electron, then I would go back and double it up. Okay, so again, these rules can seem a little confusing, but once we get into actually writing electron configurations, it tends to be a little easier. So let's start looking at some examples. The first example we're going to do is for carbon. Now, before we can write an electron configuration, we need to make sure that we know how many electrons the atom contains. Remember, the atomic number for an atom, assuming that it's a neutral atom, is going to not only tell us the number of protons, but also the number of electrons. And so if I locate carbon on the front side of my periodic table, I can see carbon contains 6 electrons. It has an atomic number of 6, therefore it has 6 electrons. So my electron configuration needs to show the placement of all 6 of those electrons. So if we think back to the rules, the first rule said we had to start at the lowest energy level. So we're going to start down here at the 1s. Each one of those circles can hold 2 electrons. And again, we're going to show those by diagonal lines. So in the 1s orbital, I have 1, 2 electrons. Okay, the 1s has 2 electrons, and again, I can visually see that with the x. So now it's time to move up to the 2s. Once the 1s is full, we jump up to our next energy level. The 2s orbital can also hold 2 electrons. And so now in total, I've placed 4 of my 6 electrons. I have 2 more to go, so now I move over to the 2p. In the 2p, I have 2 electrons to place. 1, 2. And this is going back to that bus rule where each circle can hold 1 electron, and then we double up. Okay, so if I go back and sort of retrace my steps, and I'm going to do it here in red, I can see I have placed a total of 6 electrons. 1, 2, 3, 4, 5, 6. So I've placed all of the electrons found in the carbon atom. From this diagram now, I am going to determine the electron configuration. And so I always start at the lowest energy level, which is always going to be the 1s. And in the 1s orbital for carbon, I placed 2 electrons. Once the 1s orbital was filled, I moved up to the 2s. And in carbon, the 2s orbital also contains 2 electrons. Once the 2s was filled, I moved over to the 2p, and once again, I have 2 electrons. When it comes to electron configuration, these superscripts up here should always total the number of electrons. And 2 plus 2 plus 2 does indeed equal 6 electrons. So if those numbers match, that is a good indication that my electron configuration is correct. Okay, again, just kind of to refresh what these numbers are, this number 1 here, or this 2, or this 2, represent your energy level. These S's and P's represent the orbital, and really each orbital has a different shape, so the letters represent the shape. We're not going to worry too much about those. And then the numbers here represent the actual electrons themselves. Okay, so we can use the orbital filling diagram then to come up with the electron configuration. And again, for carbon, our electron configuration is 1s2, 2s2, 2p6. From this now, we can do what is known as the orbital filling diagram. And the orbital filling diagram is going to place only the electrons found in the highest energy level. So instead of looking at all of the electrons, we're going to look at those electrons that are found in the highest energy level. Okay, if I go back to the electron configuration that I wrote for carbon, I can see that the energy levels are represented by the big numbers. And so these 2's here are the highest energy level. 2 is the highest energy level. And so my orbital filling diagram is going to look like this. I'm going to draw the circles to represent the orbitals. Okay, the 2s has 1 orbital, the 2p has 3 orbitals, and then I'm going to show those electrons in those orbitals. According to my electron configuration in the 2s orbital, I have 2 electrons, and in the 2p orbital, I have 1 electron each, or a total of 2. Okay, so my orbital filling diagram for carbon would look like this. All right, let's look at another example. Okay, here we're going to do the electron configuration for iron. Again, before we write out the electron configuration, the first thing we have to do is determine the number of electrons. So if I locate our iron on the periodic table, I can see iron has an atomic number of 26, which means there are 26 electrons in this atom. Okay, once again, I'm going to start at the bottom. Okay, and I'm going to fill my circles until I've reached a total of 26 electrons. So I start at the bottom, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, this is where we have to be careful. From the 4s, we want to jump to the 3d. So I'm already at 20, so now I'm going to go 21, 22, 23, 24, 25. One more would be 26. Okay, I've placed all of my electrons, so from here, I'm going to write the electron configuration. The electron configuration will always start the same way, 1s. In that 1s orbital, I had 2 electrons, followed by 2s, where I had 2, followed by 2p, where I had 6. After the 2p then, I went up to the 3s, which had 2, followed by the 3p, which had 6. After the 3p, I went to the 4s, which contained 2 electrons, and then finally over to the 3d, which had 6. Again, if I were to add up all of these numbers of electrons, I would see that the total number of electrons is equal to 26. Okay, so the electron configuration from iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. From here, I can do the orbital filling diagram. For the orbital filling diagram, I'm looking at the highest number. Okay, and here we want to be careful because if I look, I have an energy level of 1, 2, 2, 3, 3, 4, 3. 4 is the highest number. So the 4s is the only orbital represented in my energy level diagram here, or in my orbital filling diagram, excuse me, and it has 2 electrons. So the orbital filling diagram would look like this. Do not get in the habit of always taking the last 2, because in this case, my last one is a D, and 4 is greater than 3. So the 4s would be my orbital filling diagram. Our last example is gallium. Okay, once again, we're talking about a little higher number of electrons. I locate gallium, atomic number 31, so there are 31 electrons. If I start placing them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Here's where we want to be careful. We're at that 4s. We jump to the 3d. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, followed by 31. Okay, I'm going to translate that to my electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. After the 4s, we filled the 3d up with 10, 4p1. Okay, notice we do write superscripts of 1. We don't just assume it's 1. We definitely want to include that. From here then, I can do my orbital filling diagram. 4 is the highest. Notice I have a 4s and a 4p, so I want to include both of them. Here's my circle for my 4s. 3 circles for my 4p. In the 4s, I have 2 electrons. In the 4p, I have 1. So my orbital filling diagram for gallium would look like this. Remember, you will always have access to this energy level diagram on any test or quiz, and so there is no memorization involved with writing these electron configurations. It's simply a matter of knowing how to use the tool that has been given to you. Okay, a couple of other things we need to talk about. When we were writing electron configurations, we were representing the total number of electrons in an atom. Okay, the total number of electrons an atom contains is really not as important as what are known as the number of valence electrons. Okay, valence electrons are by far the most important electrons involved in an atom or found in an atom. Okay, a valence electron are the electrons that are found in the outermost energy level. Okay, the outermost energy level means it's farthest away from the nucleus. So if we think back to our energy level diagram, this was our 1s. Okay, here was our second energy level. Our third, the nucleus is here. And so the valence electrons would be those energy levels farthest away from the nucleus. Okay, valence electrons are the most important electrons an atom contains because they're the ones that are involved in chemical bonding, and they give atoms their properties. Okay, valence electrons, can be determined from the electron configuration or the orbital filling diagram. So for example, if we were to determine the electron configuration for sodium, we would get this: 1s2, 2s2, 2p6, 3s1. Sodium has 11 electrons. Here is my electron configuration. The highest energy level that sodium fills to is the third. It contains 1 electron, and so we would expect sodium to contain 1 valence electron. Okay, so we could write out the electron configuration, determine the orbital filling diagram in order to determine the number of valence electrons sodium has. There is also another way that we can do this, and this is by looking at the front side of our periodic table. So the periodic table's over, and this one's a little different than the one that you have, okay? But you will see that at the top of each one of these columns, so we want to think about columns as sort of running up and down, there is a number and a letter, okay? This here is known as the group number. Okay, so you will notice this first column is known as group 1A. The second column is group 2A. When we talk about group numbers, we're not going to worry about any of these, so we're going to kind of ignore this part of the periodic table. You will see we have group 3A, 4, 5, 6, 7, and 8A. Okay, these numbers are the same as yours on the periodic table. The number of valence electrons that an atom contains is going to be the same as the group number. So if you recall in our previous example, we determined sodium had 1 valence electron. If I find sodium on the periodic table, I can see sodium is found in group 1. Okay, all elements in this first column here are going to have 1 valence electron. Everything in group 2 will have 2 valence electrons. Everything in group 3 will have 3, etc., all the way up until group 8. Okay, so the group number for an atom and the valence electrons are always going to be the same. And this explains why elements in the same column have the same properties. Everything in this first column has similar chemical properties because they have the same number of valence electrons. All right, the last thing, this idea of dot diagrams. Dot diagrams are yet a third way that we can use to show the electrons in an atom, specifically the valence electrons. So if you recall, we determined that the number of valence electrons sodium has is 1. Okay, sodium atom contains 1 valence electron. And again, we could have determined that by writing out the entire electron configuration and orbital filling diagram, or we could look at its location on the periodic table. When we draw a dot diagram, we're going to represent that 1 valence electron with, as the name implies, a dot. And so dot diagrams are going to start with the element symbol in the middle. Okay, if I show the valence electrons, it has 1, so I'm going to draw 1 dot to represent that 1 valence electron. So the dot diagram for sodium would look like this. Okay, if we look at something that's a little more complex, let's look at oxygen. Okay, if we locate oxygen on the periodic table, oxygen is found in group 6, which means it has 6 valence electrons. So if I were to draw the dot diagram for oxygen, I would draw oxygen in the middle, the symbol for oxygen, and now what I want to do is I want to think about putting this oxygen in a box. Okay, so there are essentially 4 sides to my atom, or 4 sides to this element symbol. Each side can hold 2 electrons. So in this top part, I can fill 1, and when it comes to dot diagrams, we fill each side with 1 dot first, and then we double up. So here I've placed 4 electrons. Remember, oxygen has 6, so I would double up 5, 6. So without the lines, the dot diagram for oxygen would look like this. 1, oops. Let's try that again. The dot diagram for oxygen would look like this. 1, 2, 3, 4, 5, 6. Okay, and this one down here is a little hard to see. So here, let me try it again. 1, 2, 3, 4, 5, 6. So my dot diagram for oxygen shows the placement, or not the placement, but the total number of valence electrons, which again is 6. There was a lot that was covered in this video. We will spend much time, or a lot of time in class, reviewing this. This is just to kind of give you a basic idea of valence electrons, dot diagrams, electron configurations, and orbital filling diagrams.